In this video, we discuss about right linear grammars. So these are just some special types of grammars that is going to allow me to make the connection between the finite automata that we've discussed earlier in this course with the world of grammars. And I'm going to show you that in some sense that I would specify in a moment, these right linear grammars, they are equivalent. They give exactly the same languages as the finite deterministic or non-deterministic automata. And I would like to give first the definition of what a right linear grammar is. So this is really a grammar. Just like before, we have the alphabet of symbols, we have the terminals, we have the productions, and we have the star symbol. And we say that this is right linear, and I will comment in a moment what exactly does it mean, right linear. So right linear if all its productions are of the form A goes into WB or A goes into W, where A and B, as usual, we have these to be non-terminals, so they are in V minus sigma, and W is a string of terminal symbols. So what I mean by this, linearity is clear. I mean, these productions, they consist of one single symbol on the left-hand side and one single non-terminal on the right-hand side. So the linear part is clear from that. The right linear, what this means is that if you think about how these productions are going to contribute to derivations, essentially you start from the starting symbol, and that's going to give you some letters here on the left and some non-terminal, and then you get rid of this non-terminal and you're going to produce more words in here and another non-terminal, and then more words in here and then one more non-terminal, and so on. So what this means, right, it means that your production goes towards the right in these special types of grammars, and it's not like that in all the grammars. But in these ones, it is just by asking that production satisfy this form. And I also want to give right away another definition. I will say that G is a right linear grammar in canonical form. If all productions are of the form and you are asking that really you have only productions of this type. A goes into A, Y. I'm sorry, let me use just B, just so that it's just like before. Or the other one is A goes into epsilon. And just like before, A, B, they are non-terminals. And this A is just a single letter. So what I mean by canonical form is that your productions either remove one non-terminal, and instead of that you just place the empty word, or you produce one letter at a time, whereas in here you were allowed to produce longer words at a time, and you were even allowed to finish with a word. But here I'm saying when you finish, don't produce anything, and when you run a production, just insert one single letter at a time, not more than that. And I'm going to formulate here on the same whiteboard this proposition, which says for any write linear grammar there is one in canonical form generating the same language. So this is very interesting because it tells that you really can think about right linear grammars just in this form. If you have something like this, the more general form, this proposition says, don't worry about this. You can actually write one that looks much simpler and it does exactly the same job as before. And obviously there is a price to pay. When you go to a simpler structure, you are going to have more non-terminals, but we are not concerned about that in this part of the course. So here is how you prove this result. So the proof. So we have a right linear grammar, meaning that we have productions of this type, and we have productions of this type. And I'm going to produce one in a grammar in canonical form and still being right linear that essentially really replaces this production with a number of other productions, but in such a way that really there is, so applying this one once is going to be exactly the same as applying these productions in sequence. Let me just write W, maybe it's a word of this type, A1, A2, AM, with AI being terminal letters. And so the point is that this production is introducing all of them at once, and I want to introduce them just one by one. So I'm going to, instead of that production, so replace with, so instead of that production, I'm going to have this one. A goes into, and first I introduce this letter, A1, and this is going to be a new non-terminal. And the only way to produce, to get rid of this non-terminal is going to be by using this production. And then by using this production, I get rid of A2 and so on. I'm going to eventually get rid of, so this one is going to introduce the last letter of W, AM, and with the last letter I can also introduce this non-terminal B. So I'm writing here where A1, A2, AM minus 1 are new. They really have to be new non-terminals. So for every production of this type that I'm replacing, I will have to introduce new non-terminals. And the point with having new non-terminals is that the only way to get rid of A1 is by applying this production. There is no other production with A1. In that way, I make sure that to go from A to B, the only way of doing that is by by generating these letters A1, A2, AM, which was exactly what this production was doing on the original grammar. So this is, this one is going to replace this one. And for this production, I will have something very similar. I'm just going to say, well, so this production introduces all letters at once, so I can introduce them, but I will introduce them just one by one. So, for example, I introduce the first letter and say I do via this new non-terminal X1, and then X1 gives you one more letter, and so on. So eventually you get that XM minus 1 gives you AM XM, and then you have XM goes to epsilon. And so in this part, I'm going to replace this production that gives all the letters at once with this set of productions where all of these x1, x2, xm, they are new. Again, I'm talking about, and it's really essential that they are new non-terminals. And the point is, whereas this production was introducing all letters at once via just one production, this one will have to go through all of these productions, and the result is going to be the same. I just introduce first letter A1 and then first letter A2, and then I introduce letter AM, and then finally I just get rid of this non-terminal XM. And obviously there is a little bit more to this proof to show that the languages are exactly the same. But I think that I will just leave it to this. It's a very simple inductive argument why they produce exactly the same, why they generate exactly the same words. So with this construction, now I have all I need to prove the main result of this lecture. The result is really the following. A language, so L, is a recognizable language if and only if L is generated by a right linear grammar. And so this is a very interesting and not that trivial result. The proof itself is not too difficult, but if you think conceptually, on one hand, we have a language given by an accepting device, by an automaton. And on the other hand, we have the very same language given by a generating device. And again, this proof is going to be constructive. If you have the automaton, I'm going to build the grammar for you. And if somebody gives you the grammar, I'm going to show you which is the automaton accepting the same language as the grammar. So here is how this goes. So if I go into this direction, so I'm given a recognizable language, and this language is going to be, so L, because it's recognizable, this is the language of some automaton. And I'm going to take this automaton to be a deterministic finite automaton. So this is going to be of this form, Q sigma. There is a transition function and an initial state and some final states. And I'm going to just show it here visually. Remember, the automaton has this form, so you are in a state P, and your delta is telling you, hey, you have this transition from P, you go to Q with letter A. And so I construct a grammar of the required type in the following way. I'm going to have, so there are a few ideas in here. One is we have a non-terminal P for each state in Q. So that's one idea. The other idea is that the non-terminal corresponding to Q0, so Q0, which corresponds to the initial state, that's going to be the starting symbol. And productions, I will have something like this. So whenever you see a transition of this type, P goes into Q with A, I'm going to have capital P, I will have this production. For all these situations, delta of P and A goes into Q. And also I'm going to have G goes into epsilon for all situations where this state corresponding to capital G was a final state. So what I'm saying here is that for each transition you are going to have a production of this type, and for every final state you are going to have this kind of production in here. And so the intuition here is the following. As you go through your input in this automaton, you are actually generating one more letter, and you keep track of the computation via these non-terminals. And then when you are in the final state in your automaton, that gives you a way in the grammar of getting rid of the remaining non-terminal. There is no longer a need to prolong this generation because the automaton is stopping the computation in an accepting state. Let me just now prove to you that the language, if I denote by L prime, the language of this grammar, I would like to prove now that L is equal to L prime. So prove that L, which was the language of the automaton, is equal to L prime, which was the language of the grammar. And I'm going to show it to you in this way. If I take a word from L, so that means that it's in the language of this automaton, and I'm going to show you the, if W is of the form A1 all the way to AM, I'm going to show you the, accepting computation. So it starts from Q0, and then with letter A1, it goes to some state Q1, and then eventually it goes to some state QM, and that's a final state. And you see in the grammar, you will also have the following productions. Because you have this one, a transition, you are going to have this one as a production, and so you can use it in a derivation. This one is going to give you this part of the derivation. And then Q1 goes with A2 into state Q2. So that's going to give you A1, A2, Q2. And you continue in the same way until eventually you get to this state, and by then you have generated all your letters. So that's going to be QM. And simply because QM is the final state, you have that final epsilon transition. So eventually you get A1, A2, AM, which really implies that W is in L prime. So it's generated by the grammar. And the other way around is completely similar. So if I take W from L prime, meaning that there is a derivation in grammar, in grammar G, so it always starts from Q0, and really you only have productions of this type that you just introduce the letters of W one by one. Again, W is of the form A1 AM, and when you do that, you only have productions of this type. There is the symbol that you generate and some non-terminal. And then Q1 introduces one more letter, A1, A2, Q2, and so on. So eventually you have introduced, and really there are no other types of production in the grammar I have introduced. And the only way of getting rid of this final non-terminal is by applying these epsilon transitions. We only have productions of this type, and we have then epsilon productions. So that gives you A1, A2, AM. So there is no other way of deriving this word from Q0. And you see, it's exactly the same point. Just the fact that I have this production in my grammar, it means that there was this transition in the associated automaton. Otherwise, I would not have introduced this production. And then I observe that the production I'm using here is Q1 goes to A2, Q2, which means that in my automaton, I have this production, and so on. This continues. AM takes me to state QM, and simply the fact that I had a production QM goes into epsilon, it means that this is a final state. So that implies that W is in L. so that concludes the proof of the direct implication. And then we had the other implication to prove, meaning that if I have a language given by a right linear grammar, and remember, I can now assume that this grammar is in the canonical form, because if it didn't, I could really choose another grammar in canonical form that would give me the same language. So I can just as well assume that this is the grammar already in the canonical form, which really it means that you only have productions of this type. P goes into, let me just, AR, and you have productions of type, P goes into epsilon. So that was the canonical form. And I will build a non-deterministic finite automaton in the following way. I will have a state for each, so a state, if you want, small p, for each non-terminal capital P, and I will have a transition relation that consists of triples like this. I will have this one in my transition relation, if and only if I see a production of this type. Let me just write it with R so that I'm not confused. So this is R. If I see P goes into AR, then I will have PAR in my transition relation. And then finally, I will have that P is a final state if and only if we have a production of this type. And so this is really the reverse of the construction we had for the other implication. And the proof now that the language of this automaton is L is using exactly the same arguments as we had on this part of the proof. So I'm really going to skip them. It's really going over the same arguments as we had in that part of the proof. So in the end, what we are left with after all of these concepts is that on one hand we had regular expressions, and regular expressions, they are really all about structure. So they define languages, but they define in really in a way that describes the structure of that language. And we had, on the other hand, recognizable languages, which were all about computations. So they were defining languages in the way that you would do a computation on a word, and depending on the result of that computation, you would take the word in the language or not. And then finally, we had what we discussed today, and in the previous video, the world of right linear grammars, which are really about generating languages. So you really produce a language by following some rules that you have in this grammar. And so at the end of the day, we managed to prove that really these give you the very same universe of languages. But it's an impressive result, even though maybe none of the proofs were really, all that difficult. But if you think about it from this point of view, that one of them describes structure and one of them defines computations, and one of them really is a mechanism for generating things, languages in particular. The fact that we could manage to establish their equality, I think that this is the main point to take from this second half of the course. And as a matter of fact, maybe this is really the main point to take from this whole course, with a number of flavors in different parts of the course, such as the idea that deterministic and non-deterministic automata are equivalent, and all these things that we have done in terms of different types of inductions and in inductive definitions and inductive functions and all of those things. But at the end of the day, the final result that everything led to is really on this whiteboard. Regular languages, recursive languages, and right linear grammars and languages, they are really the same concept at the end of the day.